The fundamental equations of geometrical optics can be derived starting from the wave equation, which can be obtained from the theory of electromagnetism or the electromagnetic theory. The wave equation can be written in this form. If f is a wave, we can write the second derivative with respect to time multiplied by 1 over the speed of light squared, and then this is equal to the Laplacian of the field f. This can be also written in this form, so we take the second derivative of f with respect to xi and xi, like written like this, one with the upper index and the other one with the lower index, meaning that we have to sum over the index I, and we have to set this equal to 0. Then we assume that f has this form, a times e to the I times the phase psi, like this. And then we are going to put this equation here, there. So we calculate first df over dxi with an upper index or with a lower index, it doesn't really matter. This is equal to dA dxi plus ai d psi dxi times e to the I psi, and then we take the second derivative of f with respect to xi, and this is equal to second derivative of a with respect to xi plus dA dxi times I d psi dxi plus ai d squared psi dxi minus a d psi dxi d psi dxi. We also have plus I d psi dxi dA dxi, and this multiplies e to the I psi, and we know that all of this should be equal to 0, like this. Now we assume that psi is large, so all the theory of geometrical optics is based on the fact that psi, the phase of the wave, should be large. In this case, we can neglect all these terms apart from this one, because this is the only non-negligible term. It contains psi twice, as you can see, so it is proportional to psi squared. It is of a greater order of magnitude. That's what we can say. And therefore we can set d psi dxi times d psi dxi equal to 0. And this equation basically tells us that 1 over c squared d psi dt squared is equal to the gradient of psi squared, like this. Now, if we know that the wave has a constant frequency, angular frequency omega, psi will have to be of this form. It will be minus omega t plus another function psi 0 or psi naught, which depends on the vector x. So the vector x is only x, y, z. So it only depends on space. Because in this case, the wave here will have a factor of e to the minus I omega t if the wave has a well-defined frequency omega. And by knowing this equation here will become omega squared over c squared equal to the gradient of psi 0 squared. And we can also rewrite this as the gradient of c over omega times psi 0, and then we square this equal to 1. Now let's just simply call this function here psi. So I will just call it psi. It is not the same psi as defined previously, but in this case we have this simple equation gradient of psi squared equal to 1. And this is a very interesting equation, and it is the starting point for geometrical optics. So we are going to make more considerations on this equation here. In its usual form, the iconal function psi of r, or x if you want. So I used x earlier, x, y, z, or we can also use r. I mean, they are the same. I will use psi of r. This psi of r is the phase of the rays in a certain bundle passing through the point r. Now we must introduce the iconal as a function of r and r prime. Now let me tell you more about this. R and r prime are the radius vectors of the initial and end points of the ray. A ray can pass through each pair of points r, r prime, and psi of r, r prime is the phase difference of this ray between the points r and r prime. From now on, we shall always understand by r and r prime the radius vectors, 2 points on the ray before and after its passage through the optical system. If in psi of r, r prime, one of the radius vectors, say r prime, is fixed, then psi, as a function of r, describes a definite bundle of rays, namely the bundle of rays passing through the point r prime. Then psi must satisfy also this equation here, where the differentiations are applied to the components of r. Similarly, if r is assumed fixed, we again obtain an equation for psi of r, r prime. So basically what I'm trying to say is that we can consider this equation here, we can split it into two different equations. So one equation, we take the gradient with respect to r, the coordinates of r, so we get this equation here, the gradient with respect to r of psi squared equal to 1, and then we can also consider an equation of this kind, gradient with respect to r prime of psi squared equal to 1. So we have these two equations which must be satisfied because we can vary both of the endpoints of the light ray. We can be more general in this fashion without taking into account the fact that one of the two endpoints has to be fixed. The direction of the ray is determined by the gradient of its phase. Since psi of r, r prime is the difference in phase at the points r and r prime, the direction of the ray at the point r prime is given by this vector that I will call n prime. It will be a unit vector, and I will show you easily why it will be a unit vector. This is simply the derivative, or if you want, the gradient. So I can write the gradient of psi with respect to r prime like this. This psi dr prime, but this is basically just the gradient of psi with respect to r prime. So it's basically the same thing. It's just a different notation. But from the equations that we wrote here, this one actually, we can easily see that n prime squared, which means the magnitude squared of n prime, is equal to 1. So n prime is a unit vector. But n prime has a useful meaning, a physical meaning. So it will give us the direction of the light ray at the point r prime. And then at the point r, which is the first endpoint of the vector, at the point r we have another normal, n, and we'll take it to be equal to minus d psi dr. So we have to put this minus sign. This minus sign here arises because in principle we have to consider the gradient of psi with respect to r prime minus r. So this is the generic way to calculate the normal. The normal in this case, it is the direction of the light ray, and it is normal to the surface of the wave. But in this case we are keeping r prime fixed, and this gradient can be rewritten as d psi dr dot product dr with respect to dr prime minus r. And remember, we are keeping r prime fixed, so we can also add a constant inside this derivative, which is minus r prime, which is a constant, and therefore this is just minus d psi dr. It's another way of explaining this minus sign. And here we have a plus, because in this case this derivative will keep r fixed, not r prime, and therefore we are going to get this expression. So that's just the general way of explaining the signs. Therefore now we know that n squared is equal to n prime squared, which is equal to 1. The four vectors, which are r, r prime, n, n prime, are interrelated, since two of them, n and n prime, are derivatives of a certain function psi with respect to the other two, r, r prime. The function psi itself satisfies the auxiliary conditions, which are these two. So function psi satisfies these two equations here. To obtain the relation between n, n prime, r, r prime, it is convenient to introduce, in place of the function psi, another quantity on which no auxiliary condition is imposed. This can be done as follows. In the function psi, the independent variables are r and r prime. So for the differential d psi, we can rewrite d psi dr dot product dr plus d psi dr prime dot product dr prime, and this is equal to minus n dot product dr plus n prime dot product dr prime. And now we make a transformation which is called the Legendre transformation. We are going to rewrite this differential like this: d psi equal to minus d n dot r plus r dot dn plus d n prime dot r prime minus r prime dot dn prime. And now if we introduce the function chi as n prime dot r prime minus n dot r minus psi, from these two equations we easily get that the differential of chi is equal to minus r dot product dn plus r prime dot product dn prime. The function chi is called the angular eikonol, and as we see from this equation, the independent variables in it are n and n prime. No auxiliary conditions are imposed on chi. Considering that the mode of n is equal to 1 and also the mode of n prime is equal to 1, we can write, for instance, nx equal to the square root of 1 minus ny squared minus nz squared, and n prime x is equal to the square root of 1 minus n prime y squared minus n prime z squared. And if we substitute these expressions into d chi, because d chi can also be written as minus, let's call the components of r as x, y, z, and the components of r prime are x prime, y prime, z prime. So we can rewrite this as minus x dnx minus y dny minus z dnz, and here we have plus x prime dn prime x plus y prime dn prime y plus z prime dn prime z. And now that we have these two conditions here below, this one and this one, we can simply put them here and here and group together the arising terms. So we get d chi equal to minus y minus ny over nx times x d and y minus z minus nz over nx times x d and z plus y prime minus ny prime over n prime x d n prime y plus z prime minus nz prime over n x prime dn prime z. And from this equation here, we will easily find the following. So y minus ny over nx times x, this will be equal to minus d chi dny, right? Because here we have the differential of chi. So the differential of chi can be written also in this form. We have d chi over dny plus d chi over dnz plus, so we don't have d chi over dnx because we assume that nx depends on ny and z like this, so they are not independent. So the independent variables are ny and nz, or you could also have chosen nx or ny or nx and nz, but only two of them. And then here we have plus d chi dn y prime dny prime plus d chi dnz prime dnz prime. And of course, it means that since the variables are independent, we have this equation here. And similarly, we obtain also the following expression, z minus nz over nx times x equal to minus d chi over dnz. And this is the first pair of equations. Then we have another pair. The other pair is y prime minus ny prime over nx prime times x prime equal to d chi dn prime y. This is 1, and then we have z prime minus nz prime over nx prime times x prime equal to d chi over dnz prime. And this is the other set of equations, the other pair. We have two pairs. These two pairs simply consists in the relation between n prime r prime. The function chi characterizes the special properties of the body through which the rays pass. For fixed values of n prime, each of the two pairs of equations represent a straight line. These lines are precisely the rays before and after passage through the optical system. Thus, these equations, these two pairs, directly determine the path of the ray on the two sides of the optical system. We will continue from here for the next video.